All right, hello and welcome back to another video. Today we're going to do a very quick review of thermodynamics. So, as you know, thermodynamics is sort of dealing with some of the thermal parts of physics. And in a way, we can kind of summarize it like that. But I'm going to be mainly talking about the thermal side of it rather than like the different types of processes that you see in thermodynamics. So the first thing we kind of always talk about when I like to start thermal physics is to talk about the difference between heat and temperature, right? A lot of people do not really know the difference between these two, and it's kind of like a very simple and I guess you can say fundamental thing that you gotta know. So heat is simply defined as the amount of total energy that the molecules of a substance have. So it's the amount of total energy of the molecules of a substance, blah, blah, blah. And the unit of heat, which is a type of energy, is, of course, joule. Because, as you know, anything that is considered to be of energy, then we sort of say that it has a unit of joule. Temperature, on the other hand, is not necessarily the same as heat. You can give something heat, and that's going to allow its temperature to rise, but temperature by itself is actually how hot or cold something is. If I want to say it in a very simple term, actually. But something that's a bit more complex in terms of explanation, we can say it's the average amount of energy of the motions of the molecules in a substance. So it's somehow related to how fast the particles are moving in a substance, as we see in the Maxwell-Boltzmann distribution graphs later on. We basically see that the molecules that have higher energy typically have higher temperatures. But if I want to give a very simple description, it's just how hot or cold something is. And actually the units of temperature, one of the most famous and SI units for it is actually Celsius degrees. And then we have, kelvins. We also have Fahrenheit degrees, and we also have Rankine and all these other units. But the most important and the ones that we use in the A-level physics syllabus, the IB physics syllabus, is the Celsius degrees as well as the Kelvin. And notice that Kelvin does not have a degree. We just say Kelvin because it's a unit of absolute temperature. I'm going to explain that a bit later on. And then Celsius has degrees, because it's relevant to the boiling and sort of the melting point of water. All right, now let's go ahead and talk about the next thing you got to know. So we established that heat is the amount of energy that the molecules of a substance have. So the faster they move, they have a higher amount of heat. But also the average amount of energy they have is correlated to their temperature. And now we know that heat and temperature are not necessarily the same thing. So what is the next thing we have to talk about? Well, the kinetic theory is a theory that tries to describe the process of how can the temperature of something increase. Well, imagine the following scenario. Imagine we have a tiny substance. Imagine this tiny little box. It's got molecules inside of it, right? And then we try to sort of supply this substance with some amount of heat, either through a Bunsen burner, through something, anything that can give this heat. What do you think is going to happen? Well, these molecules are starting to move, right? They're going to start moving faster. They're going to start vibrating. These vibrations are technically kinetic energy. And so the faster they move, the higher, kinetic energy they have. Now, in some substances, such as solids, when you give some substances heat, well, that kind of transforms itself in the form of vibrations, because the particles start vibrating faster. In gases, the molecules, they spread out further. They start moving at greater speed. So we have more chaos in a way, because the molecules are moving faster. Their velocity is higher, and they're kind of colliding with each other more. So what is the overall idea of the kinetic theory? Well, the kinetic theory sort of says that the kinetic energy of a substance, all right, the KE, kinetic energy of a substance, determines the temperature. All right. So the temperature of a substance is dependent on its kinetic energy. And if we increase the average kinetic energy of a substance, then the temperature of that substance also increases. It is also important to note that basically whenever you apply heat to a substance, you give it energy, the molecules receive energy and they move faster. And that moving faster represents itself in the form of obviously kinetic energy, because anything that is moving faster has a higher velocity, and in turn, it has a higher kinetic energy. If you don't know why, the reason for this is because kinetic energy, in a very simple term, is measured in 1/2 of mv squared. This is the formula of kinetic energy, where m is the mass measured in kilograms, and v is the velocity or speed measured in meters per second. Now, keep in mind, the velocity and speed are not the same thing, but for, sort of like ease of understanding for you guys, I said that here you can say that v is technically speed. Now, let's go ahead and kind of take a look at a temperature scale for the Kelvin, I guess you can say, temperature unit. A lot of people don't really have an idea of how, or basically, what really describes the Kelvin unit scale. So I'm going to draw a scale here for you guys. Imagine this sort of scale. Imagine here we have a temperature of 1 Kelvin, and then we have 10 kelvins here. Here we have 10 to the power of 2 kelvins, 10 to the power of 3 kelvins, 10 to the power of 4 kelvins. And these are just estimates, so excuse me if there's anything wrong here. You can always just Google and see the exact temperatures, but if they're correct, you can use them. So 10 to the power of 7, and then here we have 10 to the power of 8. All right, so by the way, we are going to very soon, start talking about some of the topics in the IMAT. Of course, I have a lot of videos on my channel that you can watch to get yourself started if you're just starting to studying for the IMAT, or if you have your A-level papers or IB physics papers coming up. Hopefully these videos can help you out. Make sure you send them to your friends so they can also watch these, and hopefully you'll help them out and get the best score possible. Now, let's go ahead and talk about the actual temperature scale here. So here we have a 1 Kelvin, right? We can say that liquid helium has a temperature of, somewhere roughly around 1 Kelvin. And then liquid hydrogen here, again, liquid hydrogen could be around 10 to the power of 1 Kelvin. Liquid nitrogen is somewhere between 10 to the power of 1 to 10 to the power of 2 kelvins. So this is liquid nitrogen. The temperature at which copper melts is roughly about 10 to the power of 3 kelvins. So this is the temperature of copper melting. And I'm just going to skip some of the basics here. So 10 to the power of 7 is, for example, what is the temperature of the interior of the sun. So you can imagine that to be quite a high temperature. And then the temperature for a hydrogen bomb, an H bomb, is roughly about 10 to the power of 8 kelvins. So you can imagine 10 to the power of 8 to be an extremely hot temperature. Now, if you remember, I said something about the absolute unit of temperature at the beginning of this video. So what exactly is absolute temperature? All right, so we have these different units for measuring temperature in physics. We have obviously Kelvin, Rankine, Celsius degrees, Fahrenheit degrees. Andrew Celsius was the first person that came up. I mean, not really the first, but really gave us a very good unit of measuring temperature in thermal physics. So Andrew Celsius came up and said that the freezing point of pure water is about 0 degrees, right? So we know that the freezing point of pure water is about 0 degrees. Of course, if there's no impurities in it, and then we can say that it's about 0 degrees. And then Gabriel Fahrenheit, the guy that came up, he kind of said that the freezing point of pure water is actually sort of different in a way in his scale, because he said that 0 is 32 degrees below the freezing point of water. I know it's a bit confusing. That's why I don't really use it a lot in the international system, but you just kind of have to have an idea about it. And then the guy that we mainly use in the scientific papers, who actually talks about the absolute temperature, is the man that goes by the name of Lord Kelvin. He's got such a majestic name, and this guy basically comes up and says that absolute temperature is the temperature which starts with 0 at the absolute 0. So it's absolute temperature. So absolute temperature starts with 0 at the absolute temperature. At the absolute 0, actually. So what does the absolute 0 or absolute temperature mean? Well, you see, Andrew Celsius and Fahrenheit are both comparing their sort of scale to the freezing point of water. However, Lord Kelvin is not, dependent on the freezing point of water. What he talks about is the absolute 0. And what exactly is the absolute 0? Well, the absolute 0 is actually a point where all the energy from a substance is kind of taken away. right? So imagine you've got this substance, it's got this amount of energy within it. And then you take that energy away, right? You take it away. And remember, I said that according to the kinetic theory, the energy of a substance determines its temperature. Now, let's say you take away all of that energy. What's going to be left? Well, you have this substance, right? You have this substance, but it has no energy. So it has no energy. And now that it has no energy, obviously, it's going to be, at a point where it's absolutely in its purest form. So you can say that, oh my God, right now, whatever temperature it has, it starts with the absolute zero, which means that it has absolutely no kinetic energy. Of course, that's hypothetical, but basically, the basis of the Kelvin scale is the basis of absolute temperature. So at the Kelvin scale, the temperature is proportional to its temperature, which means that it has the minimum possible kinetic energy. So it's the most accurate type of scale in a way. So here we have a cautionary sign. I'm going to write what I just said. At the Kelvin scale, temperature is proportional, which means that it's directly proportional to its temperature. All right. And of course, you need to know how to convert between Celsius and Kelvins, as well as Celsius to Fahrenheit sometimes. So I'm going to write that down for you guys. If you want to convert from Celsius to Kelvins, you should add 273.15. And if you want to go from Kelvins to Celsius, you should subtract by 273.15. So I'm going to give you an example. You can try doing this by yourself, and try pausing the video. So 27 degrees, I want you to convert that to Kelvins. All right, so how do we do this? Well, 27 plus 273.15. Why am I adding? Because I'm going from Celsius to Kelvin. I got to add. I'm going to get 300.15 Kelvins. All right, and sometimes we have to convert from Celsius to Fahrenheit. How do we do that? Well, a simple formula exists for that. If you want to go from Celsius to Fahrenheit, you can actually multiply the temperature in Celsius by 1.8 and then add 32 to it. And whenever you want to go from Fahrenheit to Celsius, so the other way around, you have the temperature in Fahrenheit and you want to convert it to Celsius. So what you have to do is you have to subtract the temperature of Fahrenheit by 32 and divide by 1.8. So it's the exact opposite. And last but not least, sometimes we have a unit called Rankine. And Rankine, whenever you want to go from Rankine to Kelvin, or from Kelvin to Rankine, you just have to, for Rankine to Kelvin, you just have to divide by 1.8. And from Kelvin to Rankine, you have to multiply by 1.8. So let's do an example. Let's say you want to convert about, 200 degrees to Fahrenheit. How do we do that? Well, we want to go from Celsius to Fahrenheit, right? So we have to use this first formula. Okay, so that's going to be 200 multiplied by 1.8 added to 32. How many Fahrenheit is that going to be? Let's use the calculator for that. So 200 times 1.8 plus 32, that's actually 392 Fahrenheit. Now let's use something that's more simple, something that we see every day. Let's say, for example, 30 degrees. How many Fahrenheit is that? Usually Fahrenheit is a bigger number. So we have to, again, multiply 30 by 1.8 and we have to add it to 32. So 30 times 1.8 plus 32, that's about 86 degrees Fahrenheit. All right, so there you go. This is how you actually convert from Celsius to Fahrenheit and vice versa. Hope that you find this video useful. I'm going to be continuing this later on, talking about, the rest of the topics like specific heat capacity, specific heat, for example, latent heat, and the rest of the theories that we have in the A-level and IB physics, especially in the thermal physics. And hopefully later on, we're going to do some past papers on this. Stay tuned, support us, subscribe to us, and that way we have more motivation to post these videos and help you guys out as well. Thank you for watching. Take care.